Let's solve question 7, June 2006, about sound waves. Figure 7.1 shows how the air pressure at one instant varies with the distance along the path of a continuous sound wave. So here, what do I have? I have a sound wave. Now, as I said before, we know that sound waves, they are longitudinal waves. Sometimes we represent them like a transverse wave or a crest and a trough when we represent the air pressure with distance. Okay? So here, air pressure and distance, not the motion of the particles themselves. No, here the relation between air pressure with the distance. Okay? So the first question, what type of waves are sound waves? Now we know that sound waves are longitudinal waves. Girls, you can't say at all that they are transverse from this representation. It is wrong. Always sound waves are longitudinal waves. On figure 7.1, mark on the axis PY one point C where there is a compression in the wave. Okay, you have to do what? To mark a point to show them here. Where is the compression? Now, you remember when I explained to you this part in the video, I said that always the crest represents areas of what? High pressure. Look here, I have high pressure. High pressure, it means compression. The trough represents low pressure. Low pressure, it means rarefaction. Because in compression, it means high pressure, it means that particles are close to each other, the same as compression. In rarefaction, low pressure, it means the air particles are away from each other. Okay? Now here they said on mark on the axis PY. So here it's better, girls, to mark it here, yani R here, because they said mark it on the axis PY, and C here. Here C, and here R. Okay, good. Describe the motion of a group of air particles situated on the path of the wave shown in figure 7.1. So if you have air particles now here, how they will move? The motion of air particles. Now we are not talking about the pressure. We are talking about the motion of the air particles. How they are going to move? For sure they will move or vibrate back and forth, backward and forward, compressions and rarefactions. Clear? The last thing, the sound wave is shown has a speed of 340 meters per second and a frequency of 200 hertz. Calculate the distance represented by px. Let's look here together. Where is px? Here is px. This distance is not the wavelength. It is what? The wavelength, it's from here, for example, to here. This is one wavelength. But px is what? Half wavelength. So px is half of the wavelength. So how we can find half of the wavelength? So easy. We just find the wavelength because I have the speed and the frequency. We use the wave formula. Speed equals frequency, wavelength times frequency. We find the wavelength, then we divide it by 2. Why we divide it by 2? Because they don't want you to find the wavelength. They want you to find this distance, px. You have to know by yourself that px, it's half the wavelength. That's from here to here. Okay? That's it.